Okay, so what we're trying to do is we're going to analyze the RC circuit, experiment number 9. So we're analyzing RC circuit. So we done this similar experiment earlier, RC circuit. So RC circuit mean you have a resistor and then you have a capacitor and then connected serially. There should be a switch and then you have to have a voltage supply. If you have a DC voltage supply, let me tell you about the voltage supply. Today we're going to do voltage supply, what we call the clock type voltage supply. So I'm going to draw this symbol to represent the clock type voltage supply. CS and then voltage supply. Especially the V is actually we are using what we call the clock type. So the clock type volt supply means actually it look like the DC voltage supply, but it has a frequency. So technically what you can do, it's a square shape voltage supply. Either it's going to go on or it's going to go off, right? So which means either it has 0 voltage or after some time it's going to have some voltage value. Keep on little bit and then off and then switch on again and then off, which means this has a frequency, which means if this is the starting point, voltage on, and then keep on for a while and then switch off, and then keep off for a while and then switch on again. So if you count the time from this point to this point, so that called the period of oscillation. If you take the one over that, that's going to be the frequency of this volt supply. Okay, so that's the basic difference. Otherwise, it's technically look like the same DC type volt supply. It's not really any different than that, but it is very specific because it can switch on and off automatically within the given time. Okay, so you can decide how much time you want to switch on, how much time to switch off, and then so on. Okay, got it? Any question? No problem. Okay, then let's continue. Now, this circuit we discussed some time ago, right? So what we discussed there, if you have a capacitor, you know, capacitor act like a switch for the DC power supply. If you have this circuit, how we analyze on previously, so I have a closed loop, you apply a loop rule, that's sum of all the volt supply plus sum of all the INR equals 0. So only one voltage supply, that's our given voltage supply V, then minus I times R, and minus voltage across the capacitor equals 0. Then we know I is equal dq over dt. And then your voltage supply VC, you can write Q over C because for the capacitor, Q is equal CV, right? If you combine all of these, you can build a differential equation, right? V is equal, or you can write it down. We done this earlier too, right? I is dq over dt minus Q over C equals 0. Then you rearrange this little bit. Then you will get a differential equation dq over dt, which is equal Vc minus Q divided by the C times the R. Okay, then you rearrange this one. After you rearrange, you can get a solution for the charge on this circuit, right? So the charge as a function of time on this circuit will becomes Q0 1 minus e to the power minus t over tau. Then we discuss very specific property called the tau. Tau is actually R times C. That is called the time constant. Why it is time constant? If you put the unit for the R and C, you will get the automatically unit of tau as a second, unit of second. So that's the idea. That's how we know that should be a time constant, because you know this is e to the minus t over tau. So the e to the minus, this number should be just a number without any unit. So the tau must have the unit of time. Okay, all of those should be validated properly. We discussed this some time ago. So I would expect you to remember that. Okay. Now, since I know the charge on this circuit, so all we need to do is, if you want to measure, you can't really measure charge, but you can measure voltage, right? We can measure voltage or current, either one we can measure. Let's say I want to measure voltage. This is for the charging circuit, okay? Considering I have the voltage supply and then given power to the circuit, so we call this charging circuit. And then if I want to get the voltage, then all we have to do, if you divide this whole equation by C, then you can convert the equation into V, because Q over C, which is equal voltage, right? Voltage across capacitor as a function of time equal maximum possible voltage 1 minus exponential minus T over tau. Now this tells you, if you switch on this circuit, voltage will not automatically go into a maximum point. It actually slowly will increase to a certain number, maximum point, right? How we identify those things? How we identify those things? We can do this way. Now I have this equation. Vc is a function of t, maximum possible voltage 1 minus t over tau. Then what happens if t equals 0? Mathematically, what you get, if you put t equals 0, e to the power 0 is 1, 1 minus 1 is 0. So your voltage across capacitor when time equals 0 is actually 0. Then you take a look the other end is what happens if this goes to infinity. So if time goes to infinity, then Vc, when the time goes to infinity, Vc gonna goes to, it's gonna reach V0, because this is negative t over tau, 1 over e to the power infinity is 0. Because of that, you're gonna get V0, but I can't say equal to V0 because it's approaching V0, because the time is approaching infinity, right? Let's take a look in between values. So now, for example, I can take a look what happened if t equal 1 time constant. If t exactly equal 1 time constant, what is the voltage? So the Vc, when t equal 1 time constant, V0, 1 minus e to the minus 1, right? Because tau cancels out, e to the minus 1. If you do this part right here, you will get about 0.67. Okay, you will get 0.66 something. So let's approach that into 0.67. So which means if I wait 1 time constant, the capacitor will charge about 67% of maximum possible voltage V0. This is actually the applied voltage, okay? Applied voltage. So which means earlier, the last experiment, when you do the capacitor charging experiment, what we done, you actually make the capacitor charging data set, which means we measure voltage as a function of time across the capacitor, time versus voltage, and then we had a data set, and then we make a plot, right? We did the 2 different type of plot. One plot is Vc versus time. Then you saw it gonna go increasing rapidly and then approaching some sort of horizontal flat line. That is actually the maximum possible voltage it approaching, that is V0. Now, at that time, since we using the analysis by using Excel can't fit easily this kind of curve. What we done, we actually changed that shape of the graph into a linear by taking the ln. So the you got a function look like this then. When you get ln, it becomes negative. It's going to be look like that. By taking the slope of this graph, you actually figure out what is the tau is. So that's during that experiment, capacitor experiment. Now that is not what we're going to do today, okay? Today we can do actually this is much easier than this one. So this is only if we don't have an oscilloscope, if we have just multimeter and then stopwatch, for example. That's what we done during that simulation. We had multimeter and the stopwatch to measure the time. Then we measure the VC and the time. Then we analyze this equation by using that information, right? This whole equation. Now, today we can do this much easier. We don't need to do all of those. Instead, oscilloscope is actually can tell you exactly this graph. It can visualize that graph easily. That's what we're trying to do here. So what we're going to do, we're going to tell oscilloscope, okay, measure my output voltage and input voltage, show me how the voltage behave. Then oscilloscope is actually will show you this kind of graph. Now this is the oscilloscope. Oscilloscope will tell you input voltage gonna be clock type, right? So the clock type mean it's gonna switch on for a while and then switch off for a while and then again switch on. Okay, so it's gonna show you that graph. This is input voltage. And also it's going to tell you voltage across capacitor. So that capacitor voltage has to have a behavior look like that, right? When the voltage is 0, it is slowly starting and then slowly go to the maximum possible after some time, right? So which means initially it is 0 and then it slowly increase and then reach the maximum possible value. So this is actually charging capacitor. And whenever you switch off, capacitor will not go directly into 0 voltage. Instead, it already have a certain amount of charge, right? Because of that, it's going to take some time to decrease. So it's going to show you this kind of nice charging and discharging curves on your oscilloscope. Now, this is VC and the black line is actually input voltage. Okay, this is V input. So the V input is what we call the clock type. Either it switch off or either it switch on. Make sense? Following? And it has a frequency because frequency mean when it completing one complete cycle. So that if you take the time between those, then if you take the one over that time, then that is the frequency of this given voltage supply. Now you can see instead of doing this detailed analysis, what we done on last experiment, what we done on capacitor charging experiment, now we can do this very easily by just looking at this graph. I have charging graph and discharging graph, and the y-axis is the voltage, x-axis is the time, right? So all those information I have. For example, let's say I want to figure out the time constant experimentally on this experiment. I would like to measure time constant tau for the charging capacitor. That's the same aim we had during the capacitor experiment. Now, if I want to measure the time constant, then we know when you go one time constant on your time axis, your voltage should be increases by 67%, which means if you take a look your charging graph on your oscilloscope, charging graph going to be look like this now. That's the charging graph. This is VC, V across capacitor, and the time in second. So all I have to do, we know the maximum applied voltage, right? That is V0. I need to get 67% of V0 and then find the correlated value on your time axis. Find the V0 67%. Let's say, for example, V0 is 1 volt. If it is 1 volt, 67% of V0 means 0.67 of V applied, right? So the 0.67 of volt. So that means you find the 0.67 of volt or the 67% of the V0 and then go downward direction and then figure out this time right here. So if you measure that time, that should be equal to 1 time constant, 1 tau. So you can measure tau just by find out the time when VC is equal 67% or 0.67 of V0. That's the plan. So it's very simple because you already have the graph on your simulator, or if you're doing this experiment in class, yeah, in your oscilloscope, you actually going to see this exact behavior. Then all we have to do, figure out where's the 67% point here, and then go downward direction, and then measure what is the time value on there. Then you know how to measure the time value, because this t is generally given as division per second, right? We discussed during the last experiment how to measure anything on the x-axis. You find it out how many segments here, and then you know the division per second value, multiply by that with the segments, then you have the answer for that. That's very simple measurement. Then same thing we can do for the discharging circuit too. Okay, any questions so far? So we are working on charging capacitor circuit. Any question? So this circuit we done some time ago. Okay, you should be familiar with that. And also this analysis we discussed, this is we doing like maybe third time, because we done in class and then we done one question in the exam too. Similar thing for the charging capacitor. And now this is the third time. Okay, question. No problems. Okay, then let's continue. Okay, then let's continue. Now, you know, if you have a charging capacitor circuit connected into oscilloscope, you know you're going to observe this behavior, and then by using that particular diagram, the graph, you can actually extract the time constant. Okay, that is the plan. Let's take a look at the discharging capacitor too. Now, discharging capacitor means we have fully charged capacitor connected with the resistor, fully charged capacitor connected with the resistor, and then there's no voltage supply. Okay, you have a switch here, but there's no external voltage supply. When you close the switch, since this capacitor is fully charged, it already have charges in there, that's going to produce a current. Okay, so that's the idea. There's no any voltage supply this circuit. Fully charged capacitor connected with the resistor. Now, if you again apply the loop rule, sum of all the E plus sum of all the I and R must be equal 0. There's no any voltage supply applied, which means I have I times R, voltage drop across resistor, plus voltage drop across capacitor should be equal to 0. So this you can again do the same thing we done earlier. I is equal dq over dt plus Vc, you know, for the capacitor Q equals Cv, which means Vc equal Q over C, which is equal 0. Now again, you have a differential equation. You can simplify this little bit. dq over dt is equal minus Q over Rc. Then you can have dq divided by Q, which is equal minus 1 over Rc times dt. Now, you know, if you have a simple differential equation, to simplify that, you can integrate this, right? If you integrate, and then this is 1 over Q, this is a simple equation to solve even than the previous one. Previously, you had this equation, right? Previously, you had this differential equation to solve. Then you have to apply a substitution, things like that, because you have this function right here. But this one is much easier. It is 1 over Q is ln. If you simplify this one, you will get Q as a function of time across capacitor, which is equal simply Q0 times e to the minus t over tau. Now again, this tau is actually R times C. R times C is actually what we call the time constant, because why we call it time constant? If you take a look, the unit of R and C, units of R and C, then you will get the unit of time, unit of second. That's why we know that must be a time constant. Again, you take this equation, Q0 exponential minus t over tau, divide by the capacitance, then you will get the voltage across capacitor as a function of time. is equal maximum charge voltage times e to the minus t over tau. Now this equation look like, again, if you have initially maximum voltage, charge voltage across the capacitor, as time goes on, voltage is actually rapidly decreasing. So that is discharging capacitor. Now, if you analyze the discharging capacitor, to analyze by using this behavior, you're going to observe easily here, right? Now, this is discharging capacitor. So this side is for the charging capacitor. This side is discharging capacitor. Now, even in our last experiment for the capacitance experiment, we analyzed the discharging side too by using the equation. But today we're not going to do that. We already have the graph, right? So we're going to use this graph to analyze the time constant. To do it easily, we can do this way. So now you take this equation and then let's take a look what happened if t is equal. You can take a look all the endpoints, right? What happened t equals 0? If you put t equals 0, Vc of t equals 0 gonna be equal V0 because e to the power 0 is 1, right? And then if you take a look what happened when t goes to infinity, we see when t goes to infinity is approaching 0 because e to the power infinity 1 over infinity is 0. Because of that it is 0. What happens if t goes to 1 tau? Then your Vc when t equal tau is equal V0 times e to the minus 1 because t cancels out. E to the minus 1 is 0.33. Take a look at that number quickly. So it should be 0.37. So which means we see whenever capacitor is discharging after one time constant, that's going to be 37 percentage time or 0.37 times V0. Make sense? Follow me? Good. Any questions so far? Anybody have any problems, concern? No problem? Okay, so that means all we have to do, if I want to find the time constant on discharging capacitor, you have the circuit and then you have the graph on your oscilloscope. All we need to find it out, what is the 37 percentage of V0, that point on your y-axis, 0.37 of V0, then you go downward direction to x-axis, find the time there. If you have the time there, that should be equal to one time constant. So that's the idea. Very, very simple experiment. So these graphs is all already visible on your oscilloscope. All I have to do, find the 37 percentage and then go downward direction, find the time. So that's going to be the time constant when the discharging capacitor, when we analyze the discharging capacitor graph. Okay, good. Any question? And then during the experiment, what we're gonna do, we're gonna analyze different circuit. Okay, there's nothing else to do actually. After you build the first circuit, we're gonna analyze like 5 different type of circuits. That's the plan. So first we're gonna build the simple circuit, like you have a 1 resistor, 1 capacitor, and the switch and the clock voltage, capacitor, resistor, switch, clock voltage, and then we're gonna get one voltage, put one voltage sensor here to get the voltage in, and then one voltage sensor here to get the voltage across capacitor. So those two will give you this kind of two graphs on your two graphs look like this. One is voltage given, other one is voltage across capacitor, which show you charging and discharging behavior. So then you figure out 63 percentage, find the time constant there, time constant 1, and then you find the 37 percentage, find the time constant here, that's a time constant 2. Now, these time constant, you can calculate directly, right? You know, time constant should be R times the C. So that is calculated value. These are measured values. Then we're going to compare those two. And after we done the first circuit, then we're going to go into a different type of circuit. Technically, there's no different type. What we're going to do, we're going to change the resistor and capacitor. We can do multi-capacitor circuit, multi-resistor circuit, things like that. But it always going to be look like this. Okay, good. Any question so far? Okay, and then one other thing, when you measure time constant by using this graph now in your oscilloscope, you know there's a time axis, and then time axis will give you division per second, right? So it telling you per division, right? So this is actually some time value per division. So that's how your simulator or the oscilloscope giving you the units, right? So that means this has that square shape lines inside, right? On your oscilloscope screen, right? So they are going to be square shape like a graph sheet. It's going to be look like that. And then when you're analyzing the charging and discharging curves, you have to be careful. Right now you have a charging curve look like that, goes into a maximum point, then it's starting the discharging, right? This side is charging, this side is discharging. Now, if I want to now, you know, this should be reaching to the maximum point. So this line right here is the maximum possible V0. That depending on how much voltage you applied, right? Let's say I apply this V is equal 1.0 volt, which means your V0 is actually 1.0 volt. Now, if I want to measure the time constant by using charging circuit, if I want to measure the charging circuit, one time constant will give you 63% of V0, right? So that means you have to find the 63% of V0 means 0.63 times V0, that is 0.63 voltage. You find the 0.63 voltage relative to the given voltage right here, and then go on the x-axis, figure out where it crossing point, then you go downward direction, go this way horizontally, figure out where's the crossing point, go downward direction, figure out what's the relative time point right here, then find that time first. To find that time, what you do, how many segments you have. Let's say I have one segment here, 1.5, right? 1.5 division multiply by value of per division time. Let's say per division value is, at this point it is telling you this is example, okay? Let's say it's telling you 5 millisecond per division. Now the division cancels out. Let me write it down that also with the units. 1.5 division multiply by per division value is millisecond. 5 division cancels out. Your time gonna be 1.5 times 5 millisecond. Milli is 10 to the negative 3, right? So you have to calculate that way, okay, properly. Otherwise, you're not gonna get the time correctly, okay? Be careful when you do that calculation. Okay, any question? We used that technique last experiment. I'm expecting everybody familiar now to do that. Good, no problem. And this is for charging circuit. Now, if I want to analyze the discharging circuit, your 0 point is here, okay? For discharging circuit, you have to start from here, not from here, okay? Now, again, you find for discharging circuit, I want to have 0.37 percentage, 37% of V0 or 0.37 of V0. Find that position right here on y-axis, go horizontally until you cross discharging circuit. When it is crossed, then you go downward direction, find the time value here. Now, when you find in the time value here, the starting point of the discharging circuit is here, okay? That's the starting point of discharging circuit. The starting point of discharging circuit, which means that should be the T equals 0 point. So you measure the separation between these 2 points from here. Okay, that's the amount of segments you need. Then find again how many segments you have. If it is 1.5 or 1.3, whatever the amount of segment here, then you multiply the same division per time value. Then you can find the time constant again. Those are the time constant T1, tau 1 for the charging, and then the tau 2 for the discharging. Make sense? Following? So that means when you measure the discharging circuit, this is the amount of separation or the segments you need. For the charging circuit, this amount, okay? That's common mistake most students do when you analyze a discharging circuit. You're going to be measuring from here, assuming this is the starting point. That's completely wrong. Okay, then you will get a very different two time constant. The simple way to understand whether I have the right thing or wrong thing, these two should be about the same, tau 1 and tau 2. Because I'm analyzing the same circuit, tau is changing only if I change the ROC. If I keep the C constant and the resistor constant, there's no reason to have different time constant. Make sense? Question? Any question so far? Okay, then let's continue. So now let's build this circuit on our multisim simulator. So this thing actually useful is still, okay, this equation and then how to analyze this equation because final exam cumulative. So it can have correction from every chapter. So you have to be familiar with how to analyze this kind of equation and then how to get the answers by using this result and then so on, okay? So that's something you have to still take a look. So if you don't have any question on that, let's go and build a circuit with our multisim simulator. Any question? Anybody have any problem? Okay, so then let's go to the simulator, multisim simulator, and then take a look how it look like. So you know you use this on Monday class, you should have a login. You can use the same login. And actually you can save your circuits too if you want to, okay? If you want to revisit the circuit later when you're doing the lab report, there's an option to save every single circuit you making, okay? So let's build this circuit first. What we need a resistor. Okay, let's bring a resistor and then we need a capacitor. That also inside this resistor symbol you can see all the basic items for our circuit analysis are inside there. Resistor, inductor and capacitor, those are the three things we need for this class. Okay, one capacitor, and I need clock voltage. Okay, when you click this source, we don't need the AC type voltage now. For today we need clock voltage, this one. Okay, it should be a DC type voltage, but we need to have a clocking on that DC voltage. So which means the timing to switch on and off, that is actually clock voltage. Okay. So bring one of that and then rotate this one to have the positive towards your left. And then I need a switch. Let's bring the switch here. And also this grounding is important, any of this circuit. So let's ground this negative side properly. Okay, negative side right here should be grounded. I will ground it here. That's all. Then you connect all of these segments, right? So this should be connect to the voltage, and this should be connect to here, and this should be connect properly to the capacitor, and the capacitor other end should be connected to the other side of the circuit. So it's fairly very okay, good. Now that is our circuit. Now let's close this switch first, because then only the circuit is working properly. Now we have RC circuit. Now the one important thing, now you can technically apply any numbers. Okay, it doesn't matter what's the capacitance value, what's the resistance value, and then so on. However, when you do this RC circuit, if you do this in class, it's very difficult to observe this behavior, charging and discharging curves, by using the oscilloscope, unless you have properly fine-tuned values for resistor and capacitor, because you know these are depending on the given input frequency, right? Depending on input frequency, you have to figure out what is the time constant, and then relative to that you have to adjust either frequency input or either resistor and capacitor values. Now, which means, let's say voltage, let's apply 1 voltage, then it's easy to measure. And then let's apply frequency, which is about maybe 100 hertz. We don't need such high. And then let's change the resistor value into very larger, because you know, if I have the larger resistor, time constant is actually higher, right? So let's apply the capacitor very small. So let's apply about like 1 nano or maybe 10 nano. Okay. So those are actually given in your lab manual. If you go into table number 1, now we are working on here. So the circuit number 1, R1 100 kilo ohms, C is 10 nanofarad. Okay. We have the circuit properly. You have to measure input voltage, which means I need to have an input voltage sensor somewhere here on positive side of the given voltage. And the voltage across capacitor, I need another sensor just before the capacitor, but the positive side relative to the positive side of the input voltage. Okay, that's important, otherwise you will not get the right curves. Okay, now we have the circuit, we have the sensors, everything is fine. All you have to do is simulate this one. Click the run simulation icon, then you can see it simulating. Now you have to visualize the graph. To visualize the graph, you can click on this split button. That will show you the graph. Now all you need to do is that you remember, first thing for any oscilloscope measurement is actually triggering, right? That trigger usually should put it into the auto. Otherwise, the graph gonna be very oscillating. You're not gonna able to measure anything properly, okay? After you put it into the auto, then you can see the two graphs, right? You can see green line is actually the given voltage or the input voltage. You can see green line is the clock voltage, right? Switch on, stay for a while, and then switch off, and then stay for a while, and then so on. If you want to see this, see more graph like on x-axis, more points, what you have to do, change the x-axis. You can see now switch on and switch off many points. Okay. You can do this same experiment by applying the DC voltage only. Then you have to switch on and off manually. Now, instead of switch on and off manually, what we really do in here, we actually have set up automatically to switch on and off our input voltage. Okay. Accordingly, you can see that blue line is actually now the voltage across capacitor. You can see capacitor is starting to slowly charge and then slowly discharge. So I have charging graph and then discharging graph. And make sure you take the screenshot, all of them, because table number 1, only 2 table on this lab manual, okay? Only 2 table. First table is actually only about the circuit diagrams. So you have to save a screenshot for each of the circuit. Later, whenever you do the lab report, make sure you put the circuit picture on here, right? On table number 1, second column. It's just a circuit diagram, okay? You can either draw that physically or you can take a screenshot from here, this picture right there with all the information, values and everything, and then copy paste there later. Okay, good. You have to. So that picture on the graph, you have to include in the appendix C. That must be there too, because that's your real, this is actually part of the real data. You can include that here too, because you have enough space. You can put a small picture here of the circuit and also the graph. So technically you can copy paste, take a picture of both of them, keeping like this, both of them together, and then copy paste that into your table number 1. Then you have all the information needed there. Okay, and let's take a look. Now what we need is only in terms of calculation. There's no calculation, no anything in this lab, right? Basically what we're doing is the table number 2, we analyzing the time constant. That's all, very simple. So the values given are there. Then you know how to calculate the time constant by using R and C. And then we're going to measure that by using estimated time constant by using charging simulation curve that called tau 1, and then estimated by using discharging curve, that is tau 2. Then you take the estimated average and then compare that average with the calculated value, that is percentage difference. Very simple experiment, okay? Good, any question? Question. Okay, then let's continue. Let's take a look how to do the analysis part. Anybody have any problem? Everybody have the circuit? Good? It's working fine? Make sure all these numbers has to be properly adjusted, okay? If you don't see the graph, one quick thing to take a look is the numbers, whether you have the right numbers, resistor value, capacitor value, and the frequency, all of those are matters, okay? Anything changes, your graph will not be easily analyzed, okay? All right, any question? Okay, then let's continue. So let's take a look at the analysis part. Now what we're doing is analyzing the time constant. Let's take a look table number 1. Table 1 is actually needed only circuit diagrams. Okay, I'm going to draw it here. You can complete that later. So I have a different type of circuit and in the circuit pictures. We are working on circuit number 1. In circuit number 1, I have one resistor, which is 100 kilo ohms, and then one capacitor, which is 10 nanofarad, okay? And then you have to put the circuit picture here, including the graph, okay? So copy paste that later. It should show the circuit, resistor, capacitor, voltage supply, which is the clock type voltage, and the switch. And this point should be grounded properly. Capacitor value, resistor value, voltage value, all this stuff should be visible. And then your graph here, right? So the graph should show charging curve and the discharging curve at least. So inside here, you will see charging graph, capacitor voltage, discharging graph. All of those should be visible. And after that, let's go into table number 2. Now, table number 2, what we're doing, we analyze in the circuit time constant. Table number 2, we analyze in the time constant. Given values, circuit number 1, given value of resistor 100 kilo and the capacitor 10 nano. And then let's calculate the tau, which called the tau calculated. Unit should be second. You know how to do this calculation, right? Tau calculation is just simply R times C, right? So the R is 100 kilo, 100 times 10 to the 3 multiplied by 10 nano, 10 times 10 to the negative 6. If you do this calculation, you will get a number, right? So 3, 4, 5, 6, 10 to the negative 6 cancels out. This should be about 1 second. This is the 10 to the 10 times nano, okay, not micro. This should be 10 to the negative 9. So that means 3, 4, 5, 6. This should be 3 remainings, which means 1.0 times 10 to the negative 3 second, which is about 1 millisecond, okay? So the time constant is about 1 millisecond. Now you can see, if I try to do this experiment by using these numbers manually, I couldn't do this, right? If you get some time, take a look the experiment capacitance, charging and discharging part very end. We had actually large time constant there. We use capacitance value about like 0.1 farad, and the resistor value is about like 10 ohms. So we had about 10 or 100 ohms, I think, or 50 ohms. The time constant calculated value is about like 5 seconds or 10 seconds or so. Because we're trying to measure manually, we have to have a measurable time constant there. But this is really small, extremely small. But we can still do the experiment easily because the oscilloscope can measure actually any small time values all the way to nanosecond or even below. Okay, that's the other advantage. Okay, question. No question? Okay, then let's continue. Now, all we need to do is that measure time constant by using the charging and discharging curve, right? So I need to estimate the time constant 1 by using charging curve. So unit of second. And then I have to do the same estimation by using discharging curve, right? So I have to estimate the same one by using the discharging curve. That is tau 2 by using discharging curve, unit of second, and then I have to take the average of these two, right? TAVG, unit of second, and then I have to do the percentage difference between the average value, percentage difference between the average value and the calculated value. Okay, that is the expected percentage. Okay, that's the plan. Now let's take a look how to do the time constant by using charging and discharging graph. Any questions so far? Now for the charging graph, what we expecting? So the charging graph, you remember we discussed that earlier. Charging graph equation should be look like this, right? Vc is equal V0, 1 minus e to the t over tau. When you place t equal 1 tau, one time constant, then you can find the Vc when the time is equal one time constant equal 0.63 times V0. Now in your case, in our experiment, our V0 is 1.0 volt, which means this is going to be just 0.63 of voltage, right? Unit is volt. So I want to find the 0.63 of my charging curve. So charging curve going to be look like this, V and the time. Charging curve look like that. So I have to find what is the 0.63 value. 0.63 because maximum possible voltage is 1 volt. Okay, that's why I apply 1 volt. You can apply any, right? Depending on that, you have to calculate 63 percentage. Now this is 1.0. I want to find the 0.63. Then you go horizontally, figure out where's the crossing point. Then you go downward direction, figure out what's the time constant. You can do this easily by taking the cursor, right? If you or cursor, or you can actually move your pointer along this line. Then whenever you reach 0.63, you can read the coordinates x and y both, okay? But when you read in the coordinates this way, if you want to calculate this way, then you have to find how many number of division here. Let's say I get some division here, a number of division. Then you have to find what is the value of this x-axis, how many number of second per division on x-axis. Then to find the time right here, tau, by using the time, tau 1, which is equal number of division is a multiplied by second per division, whatever the value on second per division. Okay, let's say b number of second per division. Then this is going to be a times b second. Let's do that calculation. Now let's go here. I want to find the 0.63, right? So if you want to check the units, you click on here. Then you can see unit time per division is 1 millisecond. Okay. Now let's see, I want to find the 0.63. How to find that? 0.63. So if you try to go through here, it's not really giving me every single value. You can see points are really further away. I can't really read every single number, right? So that will be difficult to do. So which means you can actually bring a cursor. You can bring the cursor. Cursor for y-axis, and let's say I need only one cursor right now. So I need the cursor exactly 63 percentage. Now how to get the 63 percentage? Now when you move in this cursor, you can see, you can identify exactly 63 percentage. That is about 630 milli, right? So you have to get exactly cursor number 1, read here, okay? 630 millivolt. And whenever that crossing here, now you have to find what is your x-axis coordinate there. So if you get the x-axis coordinate here, then that is actually what we're looking for. Make sense? Following? So now x-axis coordinate is very close to one segment, right? One segment is about 1 millisecond, but let's try to read that. So this is very little bit of one segment, right? If you want to read it precisely, then I can change cursor type to let's take a look whether I can do it together. I can't do it together. I can have cursor either one x-axis or y-axis. Okay, let's put it into x-axis. Cursor number 1. I want to read exactly. You remember earlier the 6.3 is very close to here. Okay, you have to pinpoint that point and then read accordingly. So the time axis right now going to be about 1.03 millisecond. So that is actually division value right here. Okay, each division is 1 millisecond per division. Make sense? Following? Good. So you can measure that two ways. Okay, one is actually putting the cursor directly into y-axis and then find the 63 percentage. That's a 630 point, right? Then you have to mark that. There's no way to mark this. Okay, you have to really eyeball it and then basically remember where that crossing point is. Then change cursor into x-axis and then take a look whether that crossing point is the previous crossing point. Then read this number directly. Okay, so that is about 1.0603. So which means my time constant by using charging curve is 1.0603 millisecond, right? Millisecond. Now I need actually second units here, which means I have to multiply all of these by multiply by 10 to the negative 3 because I need the same SI units on both case. Multiply by 10 to the negative 3. So I have about the same value, but they are slightly off percentage error there. That's okay because that's our reading error, right? One of the problem here, I can't really have both cursors together to find the crossing point. So I have to remember where's the 630 point and then take that. And also you can see you can't have any lines between these two lines on x-axis or y-axis. Between that, there's a huge gap. So that gap we have to read just guessing the values. So that's the error part. Okay, that's okay. All right, question. It's a very simple experiment. Now you have to take a look the 37 percentage of y-axis, right? So I can bring this C2 to figure out the 37 percentage of y-axis. Read the y-axis value. 37 percentage mean 0.37, right? 0.37. So read it carefully, that number, and then move this cursor, C2, 37 percentage, which means 370 milli. That's the 0.37. And then change the cursor into x-axis, and then you have to remember where that crossing point is. Now, crossing point is starting from the second vertical green line to very close to the first segment right here, right? And then you change that into x-axis and then change this cursor point exactly crossing point earlier, somewhere like that. Now that's going to be 1.0603. Now you can see you have to take the picture actually at this point, then your reading and everything is actually included. Okay, now my tau from the discharging curve, which is 1.0603. It is about the same number, negative 3. You take the average going to be about the same depending on my values, 0.603 times 10 to the negative 3. Then you do the percentage difference between these two numbers. This number and this number. Okay, good. Question. Anybody have any problem? Then let's continue to second circuit and then third circuit, fourth circuit, and then so on. We have to complete all these circuits. Okay, so we have 5 different type of circuits to complete. So let's build the circuit number 2. So circuit number 2, what is difference is that anybody have any problems? Everybody okay? Measuring the time constant directly. Now you can see how easy to analyze this circuit by using the oscilloscope, right? That's the lesson actually we're doing with this experiment, because if you don't have oscilloscope, you have to measure time voltage and then make a graph, linearize the graph, and then it's a lot of work. If you have the oscilloscope, then it is very simple. Just connect the oscilloscope channels. You can see how the capacitor is behave, how it look like when it's charging, how it look like when it is charging, and then everything is extremely simple to do. That's the advantage of the use of oscilloscope. Let's take a look at the circuit number 2. Circuit number 2, you should have two resistors serially. I have resistor R1, which is the same value, 100 kilo, and then R2, which is kilo, C, which is the same value, nanofarad. Now, if you want to do the calculation, since I have the tau calculation is R times C, but now R is 2R serially connected, which means R value is 150 because you have to add them together, right? 150 times 10 to the positive 3 multiplied by 10 times 10 to the negative 9. So that will give you 345. It's going to be about 1.5 times 10 to the negative 3. So it is about now 1.3 millisecond. Now you can see if I increasing the resistances, then my time constant is slowly increased. That makes sense because time constant is just R times the C, right? If you increase the resistor or capacitor, you can increase the time constant. Now let's build this circuit. Anybody have any questions? Now we are working on circuit number 2. You have to complete both tables, okay? R1, 100 kilo, R2, 50 kilo, and C is the same value, 10 nano. And then you have to have a circuit diagram picture here, including graph and everything, okay? So wait until you put the cursors and everything to the graph, and then take the screenshot, and then later copy paste that picture into here, okay? So that's the easy way. All right, so let's build this circuit. Any question? Okay, guys, good. Let's build the other circuit. Anybody have any question? Okay, so now this is easy actually, right? Since you already know how to build it and then how to simulate one circuit, all we have to do what? If you want to do any changes, what we have to do first is stop the simulator, right? Otherwise it not let you to do any changes. All I need is one more resistor, right? So let's delete this segment and then bring one more resistor and then place it here, very close to the other resistor, right? And then change that value into 50, right? It's very simple. 50 kilo. Okay, now I have two serially connected resistance. Then you connect this segment again. That's all. Very simple. Nothing else to change, right? Everything else, keep it as it is and then simulate it again. There you go. Now you can see again your charging and discharging curves. Now you can see frequency, maybe I have to adjust a little bit because this is not reaching actually maximum charging point, right? So that will be a problem. So let us try with slightly adjusting the frequency to see whether I can get it into fully charged. So let's change the frequency a little bit. Earlier I had 100, right? Let's see with the 150. Let's try with the 150 value. still not good. It's not, you can see what I mean, right? It's not reaching this maximum point. So sometimes it's very difficult to adjust. Maybe we have to go with that error. But let's try this little bit more. Maybe we can try this with 50 hertz. Let's try with 50 hertz. Okay, so that seems to be fine now. Let's see whether it's fully charging. Okay, now it's good. Now you can see it's fully charging, right? So that's the idea. So it has to reach. So that's what I mean earlier. So you can't really just put this circuit and then just expecting it to be do everything properly. That is not the case, right? You have to always vigilant and then observe all the behavior very wisely and then adjust certain thing to get what we expecting to be what we expecting to get. Okay, so what I did, I observed the circuit, if you remember. So this is what I did. Okay, so I keep every number because my calculation is depending on this R and C. So I did not change those values. You can change those values too if you want to, nothing wrong. You do the new values for the RC, you will get the right. Now, instead of that, what I did, I adjust the frequency value. If you put the 100, there's nothing wrong. Only difference is that then you observe your curve, see the curve, the top point right here, it's not reaching this maximum possible voltage, right? See, because there's no enough time, we're going to be switching off. You can see we're going to cut off the input voltage before the capacitor reach the fully voltage, which means I need to have a more time to reach there. Inverse of time is the frequency, right? If I increase the frequency, I'm decreasing more and more time. So which means, for example, if I put 150 here, so that's what I did, right? So if I put 150 here, if I increase the frequency, mean you decrease in the time, you rerun this, then you will see it is more and more timeless. So you can see the curvature is not even reaching about 80% of charging, right? So you can see the top portion right here more and more increasing the difference between the green top point and the blue top point. Now, what we need is decrease in frequency. If I decrease the frequency, you increase in the time or the time constant of this circuit and then giving the circuit more time to reach the maximum possible voltage. So let's decrease the frequency. Let's rerun this. There you go. Now it's reaching the maximum possible voltage. Okay. So those are the fine adjustment, fine tune. So those are the things actually, the skill wise, those are the skills you gaining by doing an experiment. You may not do the capacitor circuit again in your life, but when you have the problem, how to tackle the problem, identify the situation, what parameters you can adjust, that is common for any subject. Okay, doesn't matter you do fine arts, you do dancing, or whatever the subject you do in future, engineering or electrical engineering, mechanical, civil, whatever the subject. So always you're going to get a problem to solve. When you're solving the problem, you have to identify the parameters, what parameters playing the role, how you tune the parameters to get whatever the best output or the best possible result you can get. Then you can solve that problem. That's all really. Very simple things, but those are the skills you should learn. Okay, so then it's the same thing, right? So I need to find the 63% on charging side. So let's change the cursor into y-axis. Let's bring the cursor number 1 to 63%. That's about it, right? So let's change it a little bit. I need 630 milli. That's about it. Now you can see you have to remember that point, okay? I can't really have two cursors on X and Y together. Only way to do that is actually remember that exact location where it's crossing. Then change this into, let's put the both. I need the 63 on cursor 1, 37 on cursor 2. Let's rearrange the board. That is easy to do then. simultaneously, both of them. That is about 37 actually. That's about it. 37 cursor number 2, then change the cursors into X axis. Now you have to remember, right, where was the cursors on Y? The two crossing point, first crossing point here, second crossing point for the cursor 2 there, okay? Just little bit below one segment line, okay? Let's adjust that one first. Okay, let's adjust this one first. 67, somewhere 63, somewhere very close to that point. Okay, and then cursor 2 is 37, right? Let's check that again. Y-axis, about 1/3 below this segment line right here, right? 1/3 below. So let's adjust that. 1/3 below that point, and then go back and then recheck whether those are in the right location with the Y-axis. Okay, good. Then if that is fine, then you go back to the x-axis cursors and then measure that values. That's all really. Now the cursor number 1 measuring 1.5722, cursor number 2 measuring 11.555. That is not what we needed, okay? That is from this 0, but I need only this difference, okay? This difference right here. So to get that one, actually what you have to do, you have to get rid of 1, 2, 3, 4, 5 segments. That means the 10 millisecond you have to get rid of. Okay, if you get rid of 10 millisecond, then you will get 1.554 millisecond for the second cursor. Let me write it down, that information. So when you do the second one, it's going to be look like this. This is charging curve. You still have the charging curve. And then when we measuring the discharging curve right here, so this part right here, we are not interested, okay? You have to get rid of that. So you have to measure starting from here. You have to make this is t equals 0 point. And then you find the 37% of voltage and then go this word direction, find that value, go downward direction. You have to measure the time only between these two. But when you look at it, that number which cursor number 2 is telling, so that tells you actually difference right here, okay? Difference from starting point here all the way there. There's another way to do that. There's many different ways you can actually study this simulator. This kind of studies also will be useful for your future anyway, because nowadays everything is some way is connected to the simulation and computational. Now you can do this way too. You can bring this cursor number 1 all the way to here. Then that will tell you the difference, right? You can see the difference. That difference is actually this part right here. That is another way to do, right? So then you can get little bit of error there. That's okay. That's totally our measurement error, okay? Now the difference is 1.5203. So let's do that way. That is actually better, I think. So whenever the cursor number 1 was here, you had the reading for the tau 1. That is about 1.5356. Let's write it down that part first. 1.5356 milli, okay? That means 10 to the negative 3 is still there. Now to measure this one, I have to do a little bit of adjustment, right? So what I did, I brought the cursor number 1 all the way to here. second vertical green line. Then if you look at the 1 over delta x, that is actually the time, right? So the delta x, that is actually the time between the two cursors, right? Delta x, time between the two cursors, that is now 1.5576. So that's the answer we're looking for. So that's easy to measure, right? So you have to adjust and then learn depending on the situation, right? 1.5576. 10 to the negative 3. Then get the average between these two, goes here, add those two and then divide by 2, and then compare the percentage difference between the average value and the calculated value. You can see a little bit of error, okay? That's totally fine. That is actually human error. That error, what we doing, okay? Our error. So when we measuring, our observation has those errors. Otherwise, there should not be any errors at all. Okay, question. Question. No question. Then let's continue. Circuit number 3. Okay, no problem. Anybody have any question, difficulty to measuring these things? Okay, let's do table number 3. Sorry, circuit number 3. Okay, circuit number 3. What we have on circuit number 3? Circuit number 3, I need to have 2 parallel resistors with 1 capacitor. It's the same kind of calculation, is slightly different, but it's the same kind of circuit. Only thing is that values are same, right? R1 is 100 kilo, R2 is 50 kilo, C is same 10 nano, but only difference is that R equivalent between these two is actually parallel, right? Parallel mean you have to get the 1 over addition, right? 1 over 100 times 10 to the 3, 1 over 50 times 10 to the 3. You add them and then take the negative power 1. That is the equivalent resistor, right? Then you take the equivalent resistor, multiply that with the capacitor 10 nano, 10 to the power 9. So that will give you the time constant calculated, okay? That's part you have to first do. So let's calculate that one and then see what number I'm getting. So I need to have 1 over 100 times 10 to the power 3 plus 1 over 60 times 10 to the power 3, and then outside you have to have power negative 1, right? You remember when capacitor parallel, addition is inverse, right? And then you multiply this whole thing by 10 times 10 to the power negative 9. Then you will get the time constant should be about like 3.33 times 10 to the negative 4. 3.33 times 10 to the negative 4 in second, okay? Now let's do our circuit and then figure out those things by using the charging and discharging curves, discharging graphs. Okay, question. Let's go to the circuit and then let's do a new circuit. Now again, what I need now, first you have to stop the simulator and then break this part of the circuit, and also break, you have to break this circuit too, connection between these two resistors, And then these two resistors should go parallel to each other. You can connect this way. If you connect this way, these two becomes parallel. So first you make these two parallel circuits. Right, so let's connect these two parallelly first. You know, parallel means those two should be connected to the same voltage, right? That's the parallel. So first connect these two resistances parallel to each other. And then connect to the capacitor this end all the way here. And then other end from here to the external voltage supply. Go up and then do the connection somewhere to the middle. Then it looks very nice. Look like two parallel resistors. Values are the same. Okay, there's no difference at all. Keep the same values and then first run the simulator and then see whether you can get a nice curve. Now you can see, yeah, it's charging and then it's look nice, but its curve is not visible on your charging side. See it reaching the maximum voltage immediately, right? So that means I have to change this frequency now. So let's increase this frequency a little bit and then see what you get. So change that into maybe 100 and then see how the curve is. Now it's a little bit visible, but not enough. So let's increase more. Try with the 150. You can try, you can increase more actually. Try with maybe 200. Better. 250. Much better, right? Now you go on voltage axis or the x-axis, time axis, and then change this. Okay, now you can see the curves are much visible, right? So those are the adjustment, right? So we keep the capacitance and resistance constant. We don't change at all, but we adjust the frequency value, which means we giving the circuit enough time to fully charge. Okay, and also we need to visualize the charging graph and the discharging graph properly. Okay, question. All right, then let's measure. Anybody have any problem, difficulty? Okay, now you know again the same thing, right? So you have to put the cursor first into y-axis and then bring your cursor 1 into 630 millivolt place, cursor 2 into 370 millivolt place. You can see those two are already fixed, don't change at all, right? So it is here. Now change this into, now you have to remember briefly what are those places are. Then you have to change this into x-axis and then bring C1 into 630 location. You can see now it's charging and discharging very faster. It's slightly vibrating kind of observation you can see on the curves, but it's as far as you can stable the curves, the graphs, then we are fine, okay? All right, so the 630 location, and then you have to observe the cursor number 1, 630 location, and then you can get the time value for that one. Okay, that is about 385 micro. You have to change that into millisecond or the second, directly multiply by 10 to the negative 6 to get the right answer. And then you have to compare that with the calculated value. Calculated value, I'm expecting 3.33. Now in your value you getting here 3.85. That's okay, you will get some error. That error is totally fine. As far as the error is within the margin of error, we are fine. Okay, you have to get exactly very close to the 630 location. Okay, you have to check this back with the y-axis. Remember that crossing point, change into x-axis, make sure that is exactly the same. 334.55 micro multiplied by 10 to the negative 6. 334.55, write it down, all 5 fixed to multiply by 10 to the negative 6. Second means 3.3455 times 10 to the negative 4. That exactly the same value, very close, but there's a small difference. That is our observational error. Then let's do the y-axis, right? Let's do the discharging y-axis. Remember, I'm expecting 370 roughly millivolt. That is about 37% of the maximum voltage possible, because maximum voltage is 1. Then change the cursor into x-axis, bring the cursor number 2 to the point of 370 location. That's, you have to do little bit tricky, but you have to remember that just about 1/3 before this segment line right here. Okay, 1/3 before the segment line number 1 from the discharging line. Okay, right there. Then if you take a look, that one, I need this difference. So to get the difference, bring the cursor number 1 to the second vertical green line, then take the difference. Now that is 372 micro, 372 micro, 372.94, 372.94 times 10 to the negative 6 mean 3.7294 times 10 to the negative 4. So that's close. It has an error, but it's close enough. We take in the average of these two for this one, tau average. Then we compare the average with the expected value. Okay, question. Good, then let's continue. So the next circuit, there's two other circuits, right? Those two circuits are just the capacitor changing circuit. If you take a look, anybody have any problem, difficulty doing this calculation, getting the charging, discharging curves? Everyone okay? Any question, problems? All right, so let's then start circuit number 4. Circuit number 4, we're going to go back to one resistor, but we're going to apply two capacitors serially. And then circuit number 5, one resistor, two capacitors parallelly. Okay, so let's stop this circuit, and then let's get rid of these segments, these wire segments we don't need any longer. And also R2 we don't need any longer, we need only this resistor. But now capacitors, we need actually two of them, right? First we applying two capacitors parallel to each other, 10 and 15. So I need one more capacitor. That capacitor should go here, and the capacitor value should be 15 now, right? 15 nano. 15 nano, you can type 15 and in, that's going to be automatically changed into 15 nano. And then let's connect these points. So you start from here, and then start from there, downward, and then connect here. Okay, now we have the circuit, and then everything else is fine. Keep it everything else as it is. And then first let's calculate the time constant. So I'm gonna start new page right here. and then write it down next to circuit here. Okay. Now we are working on circuit number 4. Circuit number 4 resistor is going back to 100 kilo, only one resistor. Now I have two capacitors. C1 is 10 nano and then C2 is 15 nano. Now calculated unit second. You know how calculated is R times C. To get that one, now I need the effective capacitance between these two, right? Resistor value we know 100 kilo, 100 times 10 to the positive 3, but the capacitors are serially connected, right? Now this is serially connected to capacitors. When capacitors are serially connected, equivalent capacitors is 1 over, right? So the 1 over 10 times 10 to the minus 9 plus 1 over 15 times 10 to the minus 9, close parenthesis, negative 1. So you have to do that calculation to get the right value for the calculated capacitance, right? Let's do that calculation and then see what we get. Now we have over 10 times 10 to the power minus 9 plus 1 over 10 to the power. Yeah, it's 10, right? Let's do with the 10 and then see what we get. Yeah, that's correct. Yes, let's do with the 10. 10 kilo ohms, okay, minus 9 and then multiply by 10 times 10 to the power 3. Okay, so power 1. Okay, so what we're getting is a smaller time constant now, more and more smaller, right? It's going to be 6 times 10 to the negative 5. If you do this way with the 10 kilo ohms, this is going to be 6 times 10 to the negative 5 time constant. Let's see whether that's possible to observe, because these are very extremely small. Now you can see time constant is like microsecond level, right? About like 60 microsecond. So that means the capacitor charging and discharging extremely rapidly, impossible to do manual operation, manual observation. Now let's see whether that is possible with the oscilloscope. If not, we may have to change the numbers a little bit, okay? So let's simulate this one. And then you can see here, this is possible. Why? You can see x-axis is automatically adjusting. Now you can see the each division is 500 microsecond per division, right? So that's the advantage. That's why we need oscilloscope. This kind of thing you cannot done by just manually measuring. Okay, that's the effect of the effectiveness of the oscilloscope. Okay. Now you can see again, there is a little problem, right? You can see it's not charging enough, which means maybe I have to give enough time. So you can give enough time by decreasing frequency, right? If you decrease the frequency, you can increase time. So let's decrease this frequency to maybe 200. See it reaching there, but not enough. Decrease more. Let's go back to like 150. Good enough. So see that? So that's the idea, okay? Good equation. So those are the fine adjustment. Now we are not changing any given numbers. Sorry, one quick thing. We need to change the resistor value into 10 because we calculated by using 10. 10 kilo, okay? Please change that. And then you have to change the frequency value again, okay? Actually, I have to increase the frequency because it's charging and discharging much faster rate. Let's try with 500. Not enough. Let's try with 700. Not enough. Try with 900. Still okay, measurable, but you can increase more actually. Try with maybe 1100 or maybe 1.1K. 1.1K. Yes, now it is good enough, right? So because you have to see that curvature, nice charging and discharging curves. Okay, try with 1.2 maybe, 1.2 kilo. Now you can see the whole idea is now capacitor is charging and discharging very much faster rate. So I have to change the frequency accordingly observe that behavior. Okay, you can actually increase more the frequency values. So maybe you can try 1.5 maybe, or maybe 4. Okay, good. So we have good observational charging discharging curve there. Let's measure again. So let's go back to the voltage axis, y-axis, see the two cursors. Cursors are already fixed, you don't need to change. Okay, 630, 63% of voltage, and then cursor number 2 for the discharging, 37% of the voltage. Okay, keep that there. Remember those positions, right? This is first segment, little bit above the 1/2 point, and then the second segment, and then little bit above the first line, maybe 1/4 of the first line. Okay, you can increase actually the x-axis to see whether it is clearly visible or not. One other thing you have to remember, one important thing, as a function of you changing this time per division, you can see y x-axis units must be changed. Sometimes there's a delay in this simulator, that unit is not updating properly. You see that? It is still show me 500 microsecond, but now I am in 50 microsecond per division. So it's not updated properly. To do that, maybe you have to refresh this. You can stop and then let it to run again. Then it should show the same numbers. Okay. You can see what I'm talking here is the units showing just on the x-axis on the graph, and the units on the time per division right hand side, units per time per division, this between these two arrows. Okay, so those two numbers should match to each other, otherwise we may be reading the wrong values on x-axis when we get the cursors. Okay, now we need to measure 37%, thus 1/3 beyond the first segment for the charging curve. Then the discharging curve is actually just right here. Okay, you need to remember those places and then change the axis, cursor axis, and then measure them. That's all really. So x-axis, bring it here. %63 earlier. Okay, compare that again to make sure I'm in the right location. Yeah, about it. So you can readjust this little bit more. Okay, so the value is about 61 microsecond. So let's go and take a look. So the earlier I got 60 microsecond when I do calculation. Now for the tau 1, for the charging curve, I'm getting about 61 microsecond, which means 6.1. You have to read all the numbers. Okay, 6.1243, 1243 times 10 to the negative 5. Micro is 10 to the negative 6, but there's a 61, so I can get rid of one decimal place, right? So that is tau 1 for the charging curve. Unit should be second. And then let's do tau 2. Unit second by using discharging curve. When you do the discharging curve, you know there's a couple of adjustments you have to do, right? So go back to y-axis, remember that crossing point, then bring the second cursor first, into that location. Go back to y-axis and then make sure I'm in the right location. Okay, that's 1/3 of discharging curve, 1/3 after the first segment from the second green line vertical. Okay. About right. And then let's bring this C1 into the second green line vertical. After you get that, you have to read the difference, okay, delta x. Now, delta x reading here, 59.6963. So that's close enough. So let's read that, 59.963 microsecond, right? If you write it down properly, that with the right SI units, 5.9963 times 10 to the negative 5. Okay, good. And then you take the average between those two, that goes to the tau average, tau AVG unit second, and then compare that average with the calculated value. That should be the percentage difference. Okay, good. Any question so far? So we just need to do one more circuit and then we're done. Okay, question? And make sure you take in the circuit diagram picture, a screenshot for each case, and also you taking a screenshot with the circuit and the graph together, okay? Those things, all of those circuits should go in here, okay? You have to have the circuit number 3, all the information, and then circuit number 4, all the information, and then circuit number 5, all the information, okay? That is table 1. That part of our data, okay? And all of them should show circuit picture, including the graph and then all the information. Okay, good. Any question? Okay, then let's take a look at the last circuit diagram. So I should stop the simulator, and then after that, what we need now, last circuit, the same numbers, okay, 10 kilo resistor and the same capacitance values, but now capacitance should be parallel to each other, right? That's only different, which means I have to break this connection between the capacitance. Break all of these connections. Okay, now two capacitors should go parallel to each other. Break this one too. Let's rearrange the position of the capacitor a little bit. And then first let's connect the capacitors parallel to each other. Okay, and then let's connect these two endpoints. Okay, and this endpoint. All right, now we have two capacitors, same numbers, everything is same, but parallel to each other. Make sure you take in the screenshot for each case, okay? And then let's simulate this again. Okay, click that. And it's simulating. Oh, I forgot to bring the sensor back, right? You can see the blue sensor, right? That's the other voltage sensor. You You have to click and bring it to here. Okay, let's simulate again. All right, I have both curves. Now you can see the blue line is not fully charging, right? So which means I have to adjust the frequency now again. So which means I have to give more time. So maybe I have to increase the frequency more, right? To give the more time, if you increase the frequency, you decrease in the time. You decrease in the frequency, you increase in the time, right? So let's decrease this one a little bit. So let's go maybe some number 200 hertz or so to see whether it's reaching fully charged. Is it reaching? Yes. So it means I can go a little bit more, do a little bit fine adjustment, maybe try with 250. Try a little bit more, like 280, maybe 300. Yeah, that looks better. And then you can adjust time per division to see whether you can see nicely both curves. Okay, now it looks good. Okay, and then make sure when you do all the adjustment, one thing to always keep on eye is the x-axis units right here on your graph, just below the x-axis. There is a number, it's a 500 time per microsecond per division. Same number should be showing up on your right hand side very end. You have this all the operation for the oscilloscope. There's another place called the time per division. Those two numbers should be the same. Because of it working online, sometimes there's a delay. If those two numbers doesn't match, your numbers you're reading will be inaccurate. Okay, that's all. Then again, let's go back to the y-axis. Make sure the cursor C1, 630, 63% of voltage. Cursor number 2, 37% of maximum voltage. Good. So then remember those two crossing places and then change the cursor into x-axis. Bring cursor number 1 for the first crossing place. And let's calculate first the number, then we can get a better idea what we expecting here. Then it's easy to do our measurement by knowing what number we expecting. Right now we're doing the same R value, 10.0 kilo, and then C1 is 10 nano, C2 is 15 nano, and this is now parallel capacitors, right? So which mean I need to get the RC to get the tau. So the R is same, 10 times 10 to the positive 3 multiplied by parallel capacitors mean you directly adding both of them, 10 plus 15 times 10 to the minus 9. So that will give you calculated time constant. Let's do that calculation first. So what we get, I have 10 times 10 to the power positive 3 times 10 plus 15, 25 times 10 to the power minus 9. So I'm getting 2.5 times 10 to the negative 4. 2.5 times 10 to the negative 4, which means about like 25 millisecond, right? So roughly about 25 millisecond. Make sense? Not 25 millisecond, actually 0.25 millisecond. 0.25 millisecond. Okay, now let's go back to the simulator. And then let's see about 67%. I should get about like 25, 2.25 millisecond. Or in since the simulator showing you microsecond, you can write it down this in microsecond too. Then it's easy to do the observation. To microsecond mean you have to have a 10 to the negative 6 here. To get the 10 to the negative 6, you have to multiply by 100, divide by 100, right? So which means this is going to be close to 250 microsecond. So this is going to be about 250 microsecond. So all these are adjustment, right? Manipulation. So those are the data manipulation you do according to your wish. So then you can do certain thing easier than just rely on the certain particular units. We always need the unit of second, that's the SI unit. But to do the observational properly, I would like to have microsecond here because then I can compare that with the units given on my simulator. That's all. Okay, now I'm expecting about 250 microsecond. So I'm getting 268 microsecond. Let's check this Y component. This is about exactly right here, 1/2 of the first segment. So let's go back and then revisit this one. It's about actually right location. Maybe I need more space there. You can increase that. That may be better way to do. Then observe again 1/3 after the first segment. Then rearrange this 1/3 after the first segment. And then read it again, the time constant, to see whether I get in the close enough value to 250. But don't change this until you see 250. That is not good. Okay. So that is the reading error. That reading error, it's better to have it, right? So that is our percentage error. So let's do that. About 256.67 micro. So let's write it down as it is, 256.67 microsecond, which means 2.5667 times 10 to the negative 4 seconds. So that's about close, not exactly perfectly matching, but that's good enough. Okay, then let's do time constant for discharging, right? So the discharging, we expecting 37% of voltage right here. So I need to readjust cursor number 2. Should be about like 2/3 after the first segment. Somewhere there. Okay, and then bring the cursor number 1. Cursor number 1, second vertical line of the green. Then read the delta x. Delta x is now 266 microsecond. There is an error, but that's okay. 266.18 microsecond. Then rewrite that in right SI units, 2.6618 times 10 to the negative 4 seconds. So take the average between those two, goes to here, and then percentage difference between the expected results and the tau average. Okay, question. Any question? Good, no problem. Okay, so if you don't have any problem, let's take a break and then we'll continue chapter number 14, okay? If you have any question, please ask, okay? All right, so let's take a break, 15 minutes. Let us start in 15. Of the coil, so that called the inductance. So yesterday we discussed about the mutual inductance. So the idea of that, let's take a look, chapter number 14. So yesterday we talked about the idea of mutual inductance. Mutual inductance mean if you have a two coil together,